Great, welcome back to the Codex seminar. Today we'll be hearing from Jameson Cahill, who will be speaking to us from New Mexico State. Today he's going to be talking to us about optimal Parseval frames. All right, Jameson, take it away.
All right. So this is a talk on a paper that I wrote with Pete almost a year ago now. If you look up on the archive, just that title, you'll find it. So this should, hopefully I'm going to have kind of a laid back attitude here. This was kind of a talk I probably would never have given except for this way that this situation is. So certainly feel free to interrupt me and ask me any questions. One thing with this talk is that it's a lot of little things as opposed to one big main theorem. So I probably have more slides than I'll be able to get to. So we'll just get wherever we get, and feel free to stop me along the way and ask me anything that you want. So just to get started, somehow this, most of this stuff I'm going to talk about is a manifestation of this fairly basic formula that most people learn in a first semester probability class. So if you have a random variable, the variance of that variable is the expectation of the square of the variable minus the square of the expectation. And I will refer back to this several times, but for my purposes, what this formula is going to mean for me is that if I have a condition on x that determines the expectation of x squared, then the variance will be minimized when the expectation of x itself is maximum. So we're going to see various manifestations of that kind of phenomenon. Okay, so I'm going to be talking only about Parseval frames here. I guess I didn't put the slide where I define what a frame is and what a tight frame is and what the frame operator and gram matrix is. Hopefully that's okay. I think most people here know what that is, but do be aware that I'm always talking about Parseval frames. I will talk about equal norm Parseval frames quite a bit as well, and even equiangular Parseval frames, but everything in this talk is normalized to be Parseval, not unit norm. So that affects the way that a lot of the numbers look, but just by multiplying everything by something. It just, for what I'm doing, it's more convenient to just have the frame operator be the identity operator all the time.
Yeah, so can you say in words what a Parseval frame is, Jameson?
Look, a Parseval frame is a set of vectors that gives you an expansion similar to what an orthonormal basis is. So any vector in the space can be written as a linear combination of those vectors where the coefficients are the inner products with those vectors. Equivalently, it's a frame whose frame operator is the identity operator. You know what frame operator is. And that's why I want to have Parseval. I just want to always have my frame operator be an identity operator as opposed to some different scalar multiple of the identity. Okay. Now, then if you have any frame, the gram matrix is the, so I'm going to always be having m vectors in an n dimensional space. Some people like to reverse the m and the n from the way that I'm using it. So just keep in track. So n is the dimension of the space, m is the number of vectors. So the gram matrix is the m by m matrix. M will be bigger than n always. Where the entries of the matrix are just the inner products between the different frame vectors. So in reality, everything I'm going to be talking about is actually just functions of the gram matrix of a Parseval frame. And it turns out that a frame is a Parseval frame if and only if its gram matrix is an orthogonal projection matrix. So in this case, if your frame is in an n-dimensional space and has m vectors, Parseval just means that the gram matrix is an m by m orthogonal projection onto a n-dimensional subspace.
Hey, Jameson,
So
real
pretty
quick.
much everything that I'm going to talk about, you could think of as at the level of the Gram matrix itself.
So your equation here, when you say n plus a sum, should it be m plus a sum?
No, n.
Ah, so they're not unit norm vectors because they're Parseval. Yeah.
Right.
So the sum of the energy. Thank you.
Throughout the whole talk, some things might look a little bit weird because most people often talk about unit norm things. So I'm going to be interested in this quantity, which is basically like the L1 norm of the Gram matrix, not the nuclear norm, the actual L1 norm. Like you just take the absolute value of all those inner products and add them up. But it's a pretty well-known thing that, well, since so there's the terms where I is not equal to j, and then there's the terms where you inner product the same vector with itself, and those are the diagonal terms of the Gram matrix. So on the diagonal of the Gram matrix, you just have the norm squared of the vectors. But like I just said, since it's a orthogonal projection of rank n, then the trace is just n. So basically, the diagonal terms always just contribute n, no matter what, given that it's Parseval. And then you have these off-diagonal terms. So I don't need to worry about the diagonal terms. So I will just take the sum of the off-diagonal terms. And I call that the total coherence of the frame. Yeah. So initially, what I want to look at is maximizing this total coherence. So for the first chunk of this talk, everything is going to be about what does it mean to maximize this quantity. So again, that's the sum of the absolute values of the off-diagonal entries of the Gram matrix, or just the absolute value of the inner products of all the pairs of distinct vectors from you. Okay, so this is the problem that I want to have. So first of all, again, so now I'm talking about equiangular Parseval frames. So these are not unit vectors. So equiangular Parseval frame means that the norms are all equal, and then in absolute value, the all those off-diagonal entries are all equal. Now, I think it's pretty well-known standard thing that if you want to maximize an L1 sum of a bunch of numbers, that often happens when they're all equal. Depending on what the constraints are in the problem. But so when you have an equiangular Parseval frame, you can solve in terms of n and m what that number, the absolute value of that number has to be, that they're all equal to. And if they're all equal, then you add up just that many of them, and then you get this number. So,
hey, Jameson, do you know if you're equiangular, are you necessarily equal norm?
I'm going to address that later. So yeah, so right now I'm assuming that that the norms are equal. So when I say equiangular Parseval frame, it's, yeah, I should have stated the definition, I guess. But part of the definition is that they're equal norm.
Oh, this isn't the definition. You mean that they're equal norm. Okay, thank you.
Yeah. But so if you have an equiangular Parseval frame, meaning that they're equal norm, if their norms are equal, they all have to be equal to square root of n over m. That's just because of the trace has to be n, and there's m of them. So it's not that hard to show that this number here that you get for an equiangular Parseval frame, this is an upper bound of the total coherence of any Parseval frame in terms of m and n. And in this whole talk, I'm just going to basically be assuming m and n are fixed, and you're trying to solve the problem for that given m. So, and then you'll get equality in this bound if and only if the thing is actually equiangular. So that already establishes that when equiangular Parseval frames exist, that they are the solutions to this problem. exactly the solution. There's not any other solution in those cases. But the thing is, in a lot of for a lot of given m and n, there are no equiangular Parseval frames. So you can still ask to maximize this total coherence. And that's, you know, if you think about it, at the level of the grand matrix, the grand matrices of Parseval frames are just rank n, m by m orthogonal projections. So that's a compact set, you know, a continuous function in a compact set. It's got to have some maximum. So whether or not there are equiangular ones, there's still solutions to this problem. Okay, so I'm not going to go through the proof of that, although it's a pretty straightforward calculation. And it seems like this kind of idea has been showing up in several places recently. But the main idea in the proof is that if you consider the L2 sum, so summing up the absolute value squared of all of those inner products, now that is not fixed for the off-diagonal entries. If you include the diagonal entries and you square up everything and sum them up, then that's just the Frobenius norm. And since it's a projection, orthogonal projection, you know what that is. But so the total L2 energy of the grand matrix is determined by the Parseval assumption. But that energy is not evenly distributed necessarily between the diagonal and the off-diagonal. And it turns out that the equal norm Parseval frames, they minimize the energy, the L2 energy that's on the diagonal, leaving the kind of the rest of it, the maximum amount available to the off-diagonal entries. So, you know, when you prove this, there's two inequalities that show up, and then in order to get the result, you need to satisfy both of those inequalities with equality. Very similar to how the Welch bound is derived, which we've already seen in, at least in last week's talk and maybe the week before. The thing is, here I'm starting off with the assumption of Parseval instead of unit norm or equal norm. So there's one inequality that in order to saturate it, you have to be equal norm, because you're already Parseval. And then the other inequality says that after your equal norm, then all of the off-diagonal entries have to be equal in magnitude in order to saturate the inequality. So that's how this proof goes. And there is this kind of seemingly special property that you know, equal norm Parseval frames seem to have, in that they minimize the L2 energy on the diagonal. So the initial problem that I set out wanting to solve here was, do the solutions to this problem always have to be equal norm? That seems like it might be a very hard problem and might not be true even in general. Although I will present a little bit of evidence for why maybe something like that could be true. But I think, so that's an interesting problem. If anyone has any insight into that, I would certainly be interested to talk about that. One thing we can say, so I absolutely cannot prove that. That seems like it's a tricky problem. I can get these bounds. So this upper bound was from the previous theorem. And then I can derive this lower bound on the solutions. And the way that I derive the lower bound is just by considering an arbitrary equal norm Parseval frame. Now, okay, I should say that the total coherence can be 0. It can be as small as 0. If you have a Parseval frame that's an orthonormal basis and then a bunch of 0 vectors, all of the off-diagonal entries of the grand matrix are just 0. So there are Parseval frames that have really small 0 total coherence. But it turns out that equal norm frames, you at least get this lower bound. Oh, and I'm not going to talk too much about Naimark complements here, but for those of you who know what Naimark complement is, since we're talking about Parseval frames, the total coherence of a Naimark complement pair are the same. So you get the two solutions simultaneously. That's why you have this n and n minus n.
Jameson, does this theorem require a hypothesis that you have more vectors than the dimension of the space?
Yeah, m is greater than or equal to n. or strictly greater than n.
Strictly greater, because otherwise orthonormal basis would have 0 total coherence.
Yeah. Right.
Great, thanks.
But this bound is derived, the lower bound is derived just using an arbitrary equal norm Parseval frame. So it's possible that could be improved. Well, it certainly can be improved for specific m and n, but it might be able to be improved in general. And then what I can say, I can't prove that they're equal norm, but I can prove, again, yeah, when m is greater than n, that there are some constants bigger than 0 and smaller than 1, so that the norms are stuck between these constants. And the way that you do that is you show that you can't have zero vectors in a solution. So if you have a 0 vector, you can take any other vector in your frame and replace that vector and the 0 vector with 1 over root 2 times that one, and show that the total coherence gets bigger. And then you do this Naimark complement thing to say that if you had 0 vectors in the frame, then those turn into unit vectors in the Naimark complement. So you do get some kind of control over the norms, but this is still a pretty weak statement, I guess. Okay. So coming now to the idea from that slide that I had at the beginning, this idea of variance. Oh yeah, I should say I'm going to be referring to quantities as variance throughout this talk. For it to really be the variance, you have to divide by, however many terms there are or whatever. But those are just numbers that depend only on m and n. And since I'm only worried about, I'm thinking about m and n as being fixed, I'm just not going to put those numbers there. It doesn't change anything. It just makes the formulas look more complicated if you put them there. So I understand that this isn't actually a variance here, but I'm going to call this quantity here the variance of the frame. And okay, so this number here, n over m, remember that the sum of the norms squared is always n. That comes from the Parseval assumption, and there's m of them. So n over m is the average of the norms squared of the vectors. So this quantity here, up to dividing by whatever number, this is the variance in the diagonal entries of the frame that you have. And then this number here, again, up to dividing by something, is the variance in the absolute values of the off-diagonal entries. And here, this number here is just whatever that, the mean of those numbers. So you have these two terms. You have like a diagonal variance and an off-diagonal variance. I say sort of here because I'm not dividing by the number of terms. So this equation here, this is basically a manifestation of that formula I had at the beginning, this basic formula for variance. It's not exactly that because you have these two terms and they do kind of combine together to make this thing happen. But it's a very straightforward calculation. So if you, just write it out, you will get this formula here. So that means that if you minimize this variance here, well, that's exactly the same as maximizing this total coherence, because the only thing here that depends on the frame itself is this total coherence term here, which is being subtracted. So if you want to make this be as small as possible, you want to make this be as big as possible. So somehow by maximizing this total coherence, you're minimizing the sum of these two kind of variance quantities where you have the, the variance in the norms and the variance in the angles, kind of is how I think about it. And also notice here that if the frame was equal norm, then all of the norms squared equal n over m, and this term is just 0. And then everything is coming from this term. And if it's equiangular, then in fact, this term will be 0. So equiangular frames will have 0 as this variance, but other frames will have some positive number there. Okay. So that's one observation, that maximizing this total coherence minimizes this variance. here's another quantity that looks very similar to the variance, but it's different. So I just called this the equiangular distance, just to have a name for it. The thing is here, this number that's showing up, this CMN, that's that number that you got from figuring out what would be these absolute value of these inner products if there was an equiangular Parseval frame available to you. So the main point here is that this thing does not depend on the frame. You put in the same number there for every frame. So it's a slightly different kind of measurement. And in some sense, this is kind of measuring how close the gram matrix of your frame is to the gram matrix of an equiangular Parseval frame, even when there is no equiangular Parseval frame available to you. So this seems like kind of a weird quantity to consider. But again, you just unravel that formula and you see that, again, all of this stuff up here only is just constants that depend on m and n. And the only thing that depends on the actual frame itself is this negative term with the total coherence. So you can try to minimize this equiangular distance thing also. Achieves the same result. So from this perspective, it seems very clear that this is finding the frames that are the Parseval frames that are closest to being equiangular, in the sense that they're minimizing the distance in the gram matrix to an equiangular Parseval. So one weird thing that came up when we were working on this was, if you look at this term, so again, in this equiangular distance, there's two terms. The first term is the same as what I called the variance before. The second term is different, because the second term just always has this constant here. It doesn't have the mean of these guys that depends on the frame itself. If you look at just that second term there and minimize that quantity over all Parseval frames, it turns out that if you can find an equal norm solution to that problem, then all of the solutions to the equiangular distance problem are all equal norm, and then that has the same solutions too as the other two problems that I mentioned. So this was kind of a weird observation that we came up with when we were working on this. So just to provide a little bit of insight into this, what's going on here, if you consider the Parseval frame that I mentioned before, that has just an orthonormal basis and then a bunch of zero vectors. Like I said, the total coherence of that thing is 0 because all of the off-diagonal entries of the gram matrix are 0. I mean, the gram matrix of that is just an m by m matrix with n ones on the diagonal, and then everything else is 0. So now the smallest the total coherence can possibly be is 0, and this frame achieves that. So that means that this frame has the biggest possible variance that any Parseval frame could possibly have. But if you go back to the way that I defined the variance, the second term, which is corresponding to the angles, the inner products, that entire term is 0 because all of those inner products are 0, so their average is 0. So that frame is getting all of its variance from the norm term, but it also has the maximum amount of variance that any possible Parseval frame can have, and it's coming completely from the norm part of that thing. Now, when you look at the equiangular distance, now you put that number that that's determined by m and n, that's not determined by the frame itself. So that frame no longer would be a solution if you're just looking at the second term in these sums. So it's kind of a, certainly by any reasonable way to measure these things, the frame that has an orthonormal basis and a bunch of zeros should be the worst possible Parseval frame, because you're not taking any advantage of the redundancy that's available to you. You're just having an orthonormal basis. And this reveals that in I think, kind of an interesting way. So anyway, again, the point of this is that in this theorem, you're minimizing the second term in the equiangular distance equation or formula that I had, not the second term of the variance. The second term of the variance will give you kind of nonsense solutions. Okay, so that's that. Now I want to look at other quantities that we can associate with a Parseval frame. And part of my motivation for these, depending on how much time I have, these next two things that I'm going to talk about is, there's a lot of work about these, optimizing these kind of coherence-based things for problems like compressed sensing and whatever. But the coherence really only tells you effectively about pairs of vectors in your frame. And you may want to know something about how subsets of sizes bigger than 2 behave relative to each other. So I'm going to introduce a couple of different versions of kind of something like coherence for subsets of size k, where k could be any number depending on the context. So here I'm going to assume k is less than or equal to n, the dimension of my space. And we define the k-dimensional volume is just this determinant here. That's pretty standard formula. Now, this is like, since you have less than the dimension of the space many vectors, this matrix here is like the little gram matrix of those vectors. It's not the frame operator. But anyway, you take this k by k matrix here, and you get the determinant of that as the volume squared, and you take the square root of that. Okay. So if I have a Parseval frame, I'm going to define the total k-dimensional volume to just be, you scroll across all possible subsets of size k, and you take the k-dimensional volume of each of those subsets and add them all up. And then now I'm going to consider the problem of maximizing this k-dimensional volume over the set of all Parseval frames. What can I say about this?
Hey, Jameson.
Okay, so first thing is
Jameson?
that if you consider the sum of the squares of the k-dimensional volumes, you get this number. There's a couple of ways to prove this. The way that I proved it in the paper is just by looking at coefficients of characteristic polynomials of the gram matrix. There's a more geometric way to prove this related to principal angles between subspaces, which I point a reference to in the paper. But anyway, the point is that a Parseval frame fixes this L2 sum of these volumes. Okay, so that allows me to do this thing where I'm going to get there in a minute. Anyway, so from that, you can figure out if all the k-dimensional volumes were going to be equal to each other, which in reality, that can't actually happen very often. But just for the moment, let's say that it could. You can figure out what that number would be, what number they have to all be equal to. And this is the number. Okay. So I'll call that C sub m n. And again, if you plug in k equals 1, you just get square root of n over m, which is when you have an equal norm Parseval frame, that's what the norms have to be equal to. So this is kind of a generalization of that. And then from this, you can immediately say that the minimum of these volumes has to be less than or equal to this number, and the maximum has to be greater than or equal to it. And those will be equal if and only if all of them are equal to this. So you can, this thing here if you plug in k equals 2 here, this line here, this minimum with k equals 2, essentially turns into the Welch bound after you unravel everything for Parseval frames. So these bounds here you can think of as like a generalization of a Welch bound for like k-dimensional volumes, but over Parseval frames, not over equal frames. And then, so now this is just a exactly direct application of the formula that I had at the beginning, because there's not these two different terms that have to be considered separately. So up to, dividing by the total number of terms here. If you were to calculate if you were to just list all of the k-dimensional volumes as a list of numbers and think about that as some distribution, the variance in that distribution is just this thing here. So if you want to make if you want to find frames where those volumes are all as close to each other as possible. So I'm not going to get too much into this, but it's not actually possible to get all of those volumes equal in very many different cases for different values of m, n, and k. But you can still ask to make them as close to each other as possible in some sense. And one sense that could be is minimizing the variance of the distribution of those volumes. And that is achieved by just maximizing the total k-dimensional volume. So, this shows that equal norm frames are the solutions to this for k equals 1. That's pretty trivial. It shows that equiangular Parseval frames are solutions for k equals 2, but it doesn't rule out quite yet that there aren't other solutions. So what would it mean to solve this for k equals 2? It means you want to have a Parseval frame. When you have an equiangular Parseval frame, what that means now is that in this context, what that means is that every parallelogram spanned by two of your vectors have the same area, right? So it might be possible that there are other Parseval frames that have that property, but that are not equal norm necessarily, at least right at this point. It turns out that that's not the case. But that wasn't proved yet. So the way that this goes, actually, it was this pretty clever little observation. And this really relies on the assumption of Parseval, that if you have a Parseval frame that for a given k, it has equal k-dimensional volumes for that k, then it has to have equal k minus 1 dimensional volumes. And then by iterating that all the way down to, k equals 1 means it has to be equal norm. And if it's equal norm, and then it also has equal 2-dimensional volumes, meaning areas, then in fact it has to be equiangular. So this proof of this statement is actually, I think, is kind of clever and interesting. Although it can't happen the hypotheses can't be satisfied very often, but it does at least serve the purpose of proving that if you have a Parseval frame that has all parallelograms have equal area, then it has to be equal norm, which then means it has to be equiangular. And there are some cases over the complex numbers where you can have 3, and even I think there's an infinite family of equiangular Parseval frames that have equal 3-dimensional volumes. And then there's even, I think, a finite number that have equal 4-dimensional volumes, aside from the simplex has equal every dimensional volume. Okay, so here's one of my favorite problems that I wasn't able to solve in this paper. So in general, I would like to know, is it true that if you are a maximizer of this total k-dimensional volume, does it at least have to be the case that all of your k-dimensional volumes have to be positive? somehow it seems like that's got to be the case, especially from this variance point of view. It's like you're kind of, when you solve this problem, in some sense, you're kind of packing all those volumes supposedly close together, but it doesn't rule out the possibility that maybe allowing yourself to have a few, kind of outliers that allows you to make the rest of them packed even more closely together. So this is a problem statement. I think is a good problem that I would like to know the answer to, but I do not know the answer to. And it might not be true. Okay, how are we doing on time? Okay. So this is, I said I'm not going to talk about Naimark complements too much, but I wanted to put this one little thing in here because this was like a neat little part of this paper that came up. So Naimark complement pair of Parseval frames, they're frames for different spaces. So if you have m vectors and n dimensions, then the Naimark complement will be a Parseval frame of m vectors in m minus n dimensions. And since the Grand matrix of a Parseval frame is always a projection, Naimark complement Parseval frames correspond to when those two projections add up to the m by m identity matrix. So anyway, if you're not familiar with Naimark complements, this is the only place I'm really going to talk about it, so you can ignore the next minute or so. But we know it's completely trivial that if you have an equiangular Parseval frame or an equal norm, even just an equal norm Parseval frame, that those properties are passed to the Naimark complement. Just by looking at the grand matrix, it has to be the case. It's not so obvious if you have equal volumes for a k bigger than 2, that in fact that turns out to be the case anymore. So even though I know that you can't have equal k-dimensional volumes very often, I still thought I should be able to prove that that property, when it does happen, is passed to the Naimark complement. And the way that I came up to prove it was this identity that I wasn't able to find in any book anywhere, but it seems to be a well-known identity. I found it on some like Stack Exchange or something. And the proof isn't hard, but it's not a trivial one-line thing or whatever. It's probably something that's been known for like 200 years or whatever. And it's probably just some exercise and some, type of, I could see it being an exercise in like a second semester undergraduate abstract algebra class.
What's the summation over? All subsets of J or what?
All principal submatrices of A, including A itself.
I see. You're telling me I should read your slide. Got it.
And if you plug in the numbers that I have here, because remember, if those volumes are equal, I knew what they are equal to. So somehow when you plug in those particular numbers, this is proving some kind of weird combinatorial kind of counting identity that I don't know what it is. But I don't know. I thought that was interesting that I ended up stumbling upon this weird little formula to prove the thing. Because basically, the Gram matrix of the Naimark complement is I minus the Gram matrix of your frame. And if you have equal k-dimensional volumes, you at the frame level, you have all of the lower, smaller than k are all equal to. So when you plug into this formula, they're just all the same numbers. Now, because of this minus, you'll get kind of alternating sums here. Some terms will be positive and some terms will be negative. But somehow that ends up showing that they will all end up being equal to each other.
Hey, Jameson, in the special case where A is diagonal, it looks like it's just FOIL.
Yeah, something like that, right.
So then I guess the more general thing is FOIL works over any basis.
Yeah, something like that, yeah. Maybe that's a good way to prove it. As long as, I'm only talking about positive semi-definite matrices anyway. So everything's diagonalizable. Yeah. Okay, now the last thing. So if you have just any matrix, basically the nuclear norm is just the sum of the singular values. whereas the Frobenius norm is the sum, like the L2 norm of the singular values. The nuclear norm is just the sum of the singular values. So it's not necessarily a easy thing to calculate, but it's an easy thing to define. So, well, why I came to this is I was thinking about compressed sensing kind of stuff. And then I realized that this, k-dimensional volume, it does capture some kind of notion of coherence for subsets of size k, but it didn't seem to link up very well with, compressed sensing kind of stuff. So I was thinking about, okay, what's another kind of way that I can look at this? So I thought about defining this quantity, which I call the nuclear energy in the frame, and the K nuclear energy. And that just comes from summing up all of the nuclear norms of all the subsets of size K. So, I mean, this is, if you think about it, the determinants that I was having before were just the products of these singular values. And these are the sums of them. So it's a pretty closely, but they're both related to singular values of, subsets of your frame. One thing that's kind of nice about the volume is that that's just in terms of determinants. I mean, determinants are annoying to compute, but in principle, you can write down an explicit formula for the total k-dimensional volume in terms of as a function of the entries of the frame vectors themselves. For this one, you have to actually figure out what the singular values are, which you can't express as an explicit function of the numbers in the vectors. Anyway, you can still talk about maximizing this nuclear energy quantity here. And well, it's not too hard if you consider again now the L2 version of this. So summing all the squares of the singular values. You just play this little game. Ultimately, you're just summing up a bunch of norms, or more or less, of the frame vectors, and each one shows up the same number of times. So you get this number. So just like in the case of the the total coherence, kind of, and then the volume, the assumption of Parseval fixes the L2 version of this sum. So that means I can play my same old variance game with this thing. Now, this also tells me that if all of these singular values were going to be equal, what they would be equal to, just by dividing by how many of them there are. However, the bound that you get from this is basically not meaningless, but very, very loose. Because you can never, ever achieve this equality. So here, I'm not looking at the individual nuclear norms. I'm looking at the actual, all of the singular values. So if those are all equal, basically that means that those little subset of your frame vectors was a tight frame for their own little span. And that's just not possible to have a frame where every subset of size k is a tight frame for the span. So you can still get this number, but you can never saturate the bound that you get from that number. But nonetheless, you can still play this game with the variance. So if you define the variance of just all of these singular values. So again, at this point, I'm not talking about the variance of the nuclear norms themselves. I'm actually going all the way down into the individual singular values. So maybe that's not the right thing. I don't know. Well, I mean, it's basically the same thing if you write it out. But okay, so this formula here, again, this is just exactly that same old formula that I had on the this formula for variance in terms of the expectation of the square of the variable minus the square of the expectation. If you think about it, I mean, I'm not going to say much more about this, but for people who know about doing compressed sensing kind of stuff, this seems like somehow this is really getting to the part of what you want to have. You're kind of having the solutions to this problem of maximizing the nuclear energy, which is now the same as minimizing the variance, this variance here. That means that basically that all of your singular values of every subset of size k are packed really close around whatever the corresponding mean is. And that's what you want for compressed sensing. If you think about what a restricted isometry property says, you want all of the singular values to be of every subset of size k to be living in some small interval. Now, again, just like the situation I mentioned with the volume, though, it might be possible that the actual optimizers of this thing actually have a few not so good kind of outlier singular values that then allows for the rest of them to be packed together closely. So one thing that I would be interested in is kind of quantifying in some sense how having a big nuclear energy lets you do compressed sensing good. Like I'm fairly certain that some kind of statement like that must be true, but I haven't taken the time to figure out exactly what that statement would be. Okay, now one thing I can say though, just like with the other cases, I can prove that for the case k equals 2, that when they exist, that equiangular Parseval frames do solve this problem. It's a little bit, this one's more tricky than it looks on its face. It's not just completely trivial saturating the inequality that you get from having everything equal, because you do not have that all of the singular values are equal, but you do get that the individual nuclear norms are equal. So at least the way that I proved this, the way that I wrote it out, I had to appeal back to the fact that I already knew that equiangular Parseval frames were solutions to the corresponding volume problem for k equals 2. So this, out of all of these equiangular frames are the solutions to these things, at least the way that I wrote it out, this one was actually the most complicated one, but it still turned out to be true. So, that's basically the end of what I wanted to talk about Parseval frames. I do, at the end of the paper, I do make a few remarks about equal norm frames as opposed to Parseval. So just if you're going to look at that, again, I normalized to make it matched up with the first part of the paper. I don't talk about unit norm frames. I have the norms chosen to be this number, just so that the numbers work out to be comparable to the whole front part of the paper. And just one interesting thing that I'll just mention in 1 minute is that if you consider the volume problem, maximizing the total k-dimensional volume across now equal norm frames, and when I'm using the term frame loosely here, I'm not even actually requiring them to be frames. So if you think about maximizing the total coherence over equal norm frames, that's just going to give you a bunch of copies of the same unit vector. So that's not something that you actually want to do in that case. But you can talk about volume, and you get this kind of interesting, not equality, so you only get a bound here, but you get equality if and only if you have a Parseval frame here. And if you plug in k equals 2 here, and you unravel what that means, this becomes the statement that tight frames minimize the the frame potential, as like Matt Benedetto had called it years and years ago. So this result here is like a generalization of that to higher k-dimensional volumes. So you have this upper bound on the sum of the squares of the k-dimensional volumes of an equal norm frame, and you achieve equality in that bound exactly when they're tight. And then you can get a similar statement about the total k-dimensional volume. So this theorem does tell you that equiangular Parseval frames maximize the total k-dimensional volume when they exist also over equal norm frames. And then you also get this bound here now over equal norm frames. So when you plug in k equals 2 into this and unravel it, it literally becomes the Welch bound. I have that in the paper. You can look at the steps there, but it's just straightforward calculation. So then you have this now for every case.
You said you had an infinite family for k equals 3?
I think there's an infinite family for k equals 3 over the complex numbers, not over the real number. Over the real numbers, you cannot get k equals 3. That's in this paper by that, was that Balazzo guy, you know?
Jim Salazzo?
Balazzo, yeah. Yeah.
Okay.
From a while ago now. I can dig up the paper and show it to you.
Got it. Thank you.
So, yeah, oh yeah, just one more thing. So when you're working over equal norm frames, though, because you only have a bound on this L2 sum, not an exact equality, you cannot interpret maximizing the total k-dimensional volume as minimizing the variance in those volumes. You lose that interpretation because when you write out the formula for the variance, this expression shows up there, and that's not fixed by the assumption of being equal norms. So somehow it's this Parseval thing makes this maximizing these L1 things is the same as minimizing some kind of variance in those list of things. Okay, so I will call it there. If there's any questions, I'll be happy to address them.